Chemical nomenclature is absolutely fundamental to understanding chemistry. There's no way to get around it. And it starts with the periodic table. So as in class I mentioned, you need to learn the symbol and name for elements in groups 1, 2, 13 through 18, and then the transition metals, scandium through zinc. And we'll be adding more elements as we go forward. Now, the first class of compounds that we are dealing with are the ionic compounds, where we have a cation and an anion. If it's from the periodic table as elements, it would be a metal and a nonmetal. Where things get more complicated is when we have the polyatomic ions, where it's an aggregate of atoms that have an overall charge, and they can be both cations and anions. Nomenclature for the polyatomics is also critical because, again, they're very common. You'll find them in all fields of chemistry, biochemistry, the environment, and so forth. So we have NH4 Br. Ammonium is NH4, which is +1. Bromine becomes bromide, which is -1. And again, from class, we went over the common charges based on position of the periodic table. Unfortunately for polyatomics, you must memorize both the formula and charge, as well, of course, as the name, so 3 things. The periodic table can give us some information about how we should, or what we should assume for the charge of the bromine, because it's in the halogens in group 17. For nomenclature, again, bromine becomes bromide, so this would be ammonium bromide. So we have a cation and an anion, and I'll put some more examples for you to practice here and post the answers later. But please keep reading through the first 3 chapters of the textbook and learn chemical nomenclature, symbols from the periodic table of the elements, as well as the polyatomics. And these examples, I'm literally just making them up as I go along. There are, an infinite number of possible chemical compounds. We'll see that we can understand nomenclature by following trends, and it starts with understanding, again, charges. Potassium is in group 1, so it's +1. Cyanide is one of our polyatomics. It's -1. Now, in this case, I've given you the formula, and I'm asking for the name, but I could do it the other way around. Now, before I write this out, what I would really recommend, pause the video, KCN AlNO3 in parentheses, CaI2, MgOH2 in parentheses. Try and write these names. See if you can do it yourself. One thing I should mention for nomenclature, if you notice, we have these parentheses around these species, and that's because with polyatomics, if you have more than one, you need the parentheses to clearly indicate how many of each polyatomic ion you have. For our first example, potassium cyanide. So cyanide is, again, one of our polyatomic ions. Aluminum with nitrate. So this will be aluminum nitrate. But aluminum is in group 13. Aluminum can have different charges. +3 is the most common, but it's possible that an element in group 13 could have a different charge. So we explicitly write aluminum, and then in parentheses 3, the Roman numeral 3, then nitrate. This 3 tells me the charge of the aluminum, or its oxidation state. CiI2, calcium iodide. iodide. I think I said that more like iodine. So iodine becomes iodide. Yeah, you have to be careful when you say this to make sure you pronounce it correctly. Again, with the halogens, we would expect iodine, I2, to form a -1 charge. So the calcium is +2, and each iodine is -1. Now you might say, well, how come I'm not calling this calcium 2 iodide? And it's because in group 2, the elements in group 2 form +2. They do not typically form other charges. So for potassium and calcium, we can just leave the name as it is, but for aluminum, we need the Roman numeral. MgOH. So OH is hydroxide, one of our polyatomics, and Mg is magnesium. So this would be magnesium hydroxide. Both within the chapter and at the end of the chapter with the problems, your book has many examples of nomenclature. Take the time, practice them, and don't do it passively like you're doing now, just watching me work them. Put the names on one piece of paper and then leave it blank and then come back later and then write in, or vice versa, or put the formula, write the name, and then vice versa. So I'll give some examples where I'll give you a chemical name and then So sodium phosphate. Phosphate is a polyatomic. Write that chemical formula down. Let's see. Strontium nitrite. Again, take the time, pause or whatever, write that down. Again, I can't stress enough how important it is in nomenclature to be able to seamlessly go back and forth from the name of the compound to the chemical formula. Ammonium hydroxide. Ammonium and hydroxide are both polyatomic species, but there's nothing wrong with having a chemical formula of two polyatomic species. In fact, that's actually quite common. Sorry. You can capitalize the first letter. That's what I was about to do, but it's not necessary. So indium 1 sulfate. So these are just 4 examples for nomenclature. We'll be doing a lot more. One thing that we'll start on Monday is nomenclature of the transition metals, which are the elements in groups 3 through 12. In that case, just like with indium where we have to put the charge, we'll have to do that explicitly as well. Again, take the time before looking at the rest of the video, pause the video, and go ahead and see if you can put down these formula. Sodium phosphate. Sodium is a +1 cation. Phosphate is a -3 polyatomic anion. Therefore, we need 3 positive charges to 1 phosphate. This is often called the crossover method, where you bring the charge diagonal down, bringing 1 here, obviously 1 phosphate, -3, we need 3 sodiums. However you do it, the cation and the anion, their charges must sum to 0. So that's how I know sodium phosphate is Na3PO4, 3 sodiums, 1 phosphate. Strontium nitrite. Strontium is a +2 cation. Nitrite is NO2 -1, +2 -1, so I need 2 of the nitrites. Because it's polyatomic, we put it in parentheses. If you left off the parentheses, it would be NO22, right? In other words, you need to distinguish that it is the 2 of the nitrites. Ammonium hydroxide, again, 2 polyatomics. Ammonium is +1, hydroxide is -1. By the way, for your benefit, I am showing the charges explicitly. When you write the formula, that's perfectly acceptable. Ammonium hydroxide, no charges are put up above. But again, as you are learning this, take the time, be as absolutely systematic as possible to get the best result. Indium 1 sulfate. So the indium is +1, that's given to you, and sulfate is a polyatomic that is -2. So the formula will be 2 indiums, 1 sulfate, so In2SO4. Again, we have to have charge balance for this compound to exist. It has to be neutral.